Hi class. Today we are finally getting to our full hypothesis test, which is section 9.5. Once again, I have our 4 steps for our hypothesis testing procedure. And just a reminder, 9.1, in section 9.1, we learned how to write our null and alternative hypothesis statements with the claim indicated. In 9.4, we learned how to write the conclusion or the answer to whatever our claim was in non-technical terms. And today, we're finally going to get to work with the numbers. So in 9.5, we will do the full hypothesis test. We're going to learn how to find something called the test statistic. We're also going to learn how to find something called a p-value, which is a probability. And I will show you one example using the formula, but for the most part, we're going to use the calculator. And I've noticed the longer that I teach statistics, the more I end up using the calculator. The calculator is going to save you time with those calculations. Now, I do like to show you the formula first so that you can see the logic and the concept where it's coming from. The calculator is just going to save you a lot of time. Okay, so our first definition is something called the test statistic. It's a value used to make a decision about the null hypothesis. And you will be calculating this from the sample. And you can find your test statistic using a formula or the calculator, as I said. If we're using the calculator for a proportion, you will use the 1 prop z test. You're used to seeing a 1 prop z interval from chapter 8. When you have one proportion for a hypothesis test, you'll use a 1 prop z test. For a mean, you will use a t-test. So again, just like in chapter 8 when we did the intervals, if we were doing an interval about a mean, it was a t-interval. Now, because it's a hypothesis test, it's a t-test. And we talked about when we did our confidence intervals that there are intervals and tests using z, a z-test and a z-interval. In order to do those tests, you need to know the population standard deviation, which it's very uncommon realistically to know your population standard deviation, especially since you don't know your mean. So in all of the problems we're going to work on, sigma will be unknown, the population standard deviation. Okay, you will know the sample standard deviation, or you will be able to find it. So all of the means will be using a t-test, and all of the proportions will use a 1 prop z test. The formulas are listed here. They are also on your or in your formula packet on page 2. So if you look in your formula packet, on page 2, you'll see the formulas. Most people, again, prefer to use the calculator, okay? If we look at the formula, you'll see some familiar notation. P hat, remember, is your sample proportion, which is x over n. P is your population proportion. And Q, remember, is the complement 1 minus P. N is your sample size. For this one, we have X bar is your sample mean. Mu is your population mean. S is your sample standard deviation. And then N, as I said, is your sample size. Again, we're going to use the calculator. So I will show you one example with the formulas, but for the most part, the calculator is the way to go. Okay, we've talked about critical region before. When we were talking about the critical region, remember we talked about if it's greater than, it's over to the right. If it's a less than, it's over to the left. So on the critical value, these are the extreme values. Significantly high, significantly low, significantly different. So these can be left, right, or two-tailed test. And we drew the pictures when we were writing our hypothesis statement. Okay, now we get to something new, the significance level. And you'll see I have alpha in here. And we've talked about alpha before. The significance level is the probability that the test statistic will fall into the critical region when the null hypothesis is actually true. And when you read that, you're probably thinking, what the heck does that mean? The definition probably doesn't provide clarity. Here's what it means. It's the level of significance. How high does it have to be? How significantly different? It's similar to when we look at an outlier. How far does it have to be considered an outlier? So if we were talking about a significance level of 0.01, that would mean it would need to be in the most extreme 1%. So if I was looking at this greater than one right here, it would be the top 1%. The significant values are in the highest 1%. Or 0.05, the highest 5%. Or 0.10, the highest 10%. If we were talking about a less than, it would be the lowest 1% and the lowest 5% or the lowest 10%. The not equals, it's the two tails together. And when you look at this, alpha is typically given to you. The significance is typically given to you. If it's not given, so let me put this here. If not given, use alpha equal to 0.05. And I want you to think about something. Remember with our probability, our unusual values, unusual and also unusually high or unusually low, the probability was less than 0.05. So we talked about this chapter bringing together lots of different concepts. We still have probability, we have normal distribution, we have unusual. Okay. The next new term is called p-value. And it says the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data. And then it has this statement right here. If the p-value is less than alpha, reject HO. That's going to help you make your decision. Am I going to reject? Am I going to fail to reject? And if we go back up to this list, if, oops, need my highlighter. If the p-value is less than alpha, reject. If the p-value is greater than or equal to alpha, then fail to reject. Typically, your p-value, you're going to round to 4 places. So typically, it's either less than or greater than. It's very rare for that equal to come in. Okay. So remembering, we want small p-values. You're going to get some really, really tiny p-values, which means you reject your null hypothesis. And typically your claim is in your H1, and that means you're supporting your claim. So you're going to get really used to seeing these tiny values. Watch for them. And when we do our examples, you'll see that as well. Okay. I want to give you a big picture of the process we're going to do. And this can be a little tricky. And right now you're probably looking at these new terms and feeling like, ooh, what's going on here? That would be perfectly normal. So continue to take your notes and continue to think about this. As we start doing the problems and applying it, it will start to come together. So the big picture here, I want you to think about, remember when we did the M&M activity? We talked about, are the bags of M&Ms significantly different? And some were significantly high, and some were significantly low, and some were the same. So let's say we had a situation with a greater than. So our H1, our alternative hypothesis, had a greater than. Our critical value, or our critical region, excuse me, for a greater than is over here. And I actually want to use my highlighter in here. So my critical region is, see if I can get, no, it's not going to work. It only wants to highlight letters, apparently. Okay, so this would be my critical region. And depending on my significance level, maybe this is, how great does it have to be? How much higher does it have to be? Does it have to be in the top 1% or the top 5% or the top 10%? That will be determined by your alpha, by your level of significance. You're going to calculate a test statistic from your sample. And that test statistic will either fall to the left or it will land in that critical region. So I could kind of shade that a little bit. Okay. Prior to calculators, when I took this class, we had calculators, but we didn't have graphing calculators. And what we would do is we would find this cutoff value. And then we would decide, is the test statistic to the left of that, in this case? And we would say, oh, it's not significantly higher, so we'd fail to reject. If the test statistic was in the critical region, that would mean, oh, our values in our sample are significantly higher, then we would reject. That method is called the traditional method. And it used to be that p-values were a little more challenging to find. Now it's easier to find p-values. So the method we're going to use with the p-value, we're not going to get this critical value right here. What we're going to do is we're going to get a p-value. And the calculator's actually going to find it for you. I'll show you how we would do it by hand as well. When you get the p-value, basically what it does, wherever your test statistic is, we're doing a greater than, so it would get the area greater than that value. And you can see here, I think, that if your test statistic is not in the critical region, the p-value is going to be bigger than alpha. If your test statistic, I'm going to take this out. Let's say you're, oop, took out more than I wanted. Let me get that guy. See if we can get that kind of drawn in. Okay. Let's say your test statistic was in the critical region. Then what would happen when you get your p-value? You're finding the area to the right. Do you see that that area would be smaller than the critical region? It's contained within the critical region. That's why if the p-value is less than alpha, alpha again is your 0.01 or your 0.05 or your 0.10, then you reject the null hypothesis. And it would mean, yes, whatever we're looking at is significantly higher. If it were here, can you see that that area would be bigger than the critical region? So if the p-value is greater than alpha, then reject. And it's interesting, depending on the book, because we're using that different book, some books put the equal here, some books put the equal there. Most of the time, you're not going to come up with the equals because you're not going to get exactly 0.05. You're going to get, 0.0536 or 0.05003 or something like that. So I discovered that with this book, that it does a little differently than the last book. Okay, let me give you another big picture. Because right now you might be kind of scratching your head a little bit going, okay, let's say our null or our alternative hypothesis had a less than. So here, our critical value, our critical region, I keep saying that, our critical region would be over here, significantly less than. So this is our critical region. We're trying to decide from our sample, are these values significantly lower? So if we were talking about those M&Ms, were the bags significantly less? Did they weigh less than this M&M Mars company was claiming? So we would get our test statistic using the formula or the calculator. And your test statistic could end up in the critical region or not. Let's say it's in here. We don't know which one it is. So when we get our p-value, if it's out here, your p-value will be greater than the critical region. That area is bigger. Area is the probability. And we would fail to reject HO. If your test statistic was in here, because we're going less than, we would look significantly lower. See how that area is smaller than the area of the critical region? We would reject HO. Okay, last example. And then we'll actually do some number crunching. If we had a not equal, I just want you to visualize this. This is a two-tailed test. So you have this section or this section. The critical region could be significantly higher or lower. Those two together make up your alpha. So those two together are 0.05 or 0.01 or 0.10. Okay. When you get your test statistic, it could be in here, or it could be here or here. When you get your p-value, if it's in here, if it's here, if it's here. Those can be a little trickier because you have to double what you get. Again, the calculator is going to do it for you, so I don't think you're going to have that worry so much. But we do have to consider there's two. Okay, so p-value will be calculated in the calculator. We could use normal CDF to calculate it as well, and I'll show you that in our first example. So big picture, we're trying to decide, is there a significant difference? How significant? Depends on this level of significance that's given to us in the problem.